Hello and welcome to Unit 2 Phases, Lecture C, Gas Laws Part 2. So let's check it out. Today's lecture is basically going to be practicing what we already know about the gas laws. So looking at some problems and examples using Boyle's Law and Charles's Law. Those are the two big ones that the state goes over. And then we'll also talk about partial pressure and something called Graham's Law and how we can use the density of gases to help us figure out some other information. So quick review, what was Boyle's Law? Boyle's Law was the relationship between the pressure and the volume of a gas. So relationship between pressure and volume. It says that it varies inversely. That means as one increases, the other must decrease in order for the value to stay the same. If we look at the equation here, it's set up slightly different than when we looked at our reference table and we talked about the combined gas law. So let's go back to the combined gas law. And we said we were going to ignore what stayed constant. And so for Boyle's law, if temperature was constant, this is going to be Boyle's law right here, P1V1 equals P2V2. So you're multiplying. And there's an inverse relationship. If we go back to our lecture notes and look at the way that equation is set up, it's set up as a proportion. V1 over V2 equals P2 over P1. So to do this as a proportion, you need to remember that it's an inverse relationship and that you're going to flip them, that you're not going to set them up in the same direction. You're not going to have V1 and P1 at the top. You have to remember to flip it because it's inverse. This is why I prefer using the combined gas law equation and just ignoring what stays constant. This is going to give you mathematically the same thing as saying P1 over V1 equals P2 over V2. You've basically already done the cross multiplication step. So if you cross multiply this, you end up with this. So just use your combined gas law and ignore the temperature because the temperature stays constant. You should know what a graph of Boyle's law looks like for an ideal gas. So that perfect gas with no volume, no size, no mass, no attraction for other particles, no loss of energy. Perfect ideal gas, you would get a perfectly straight line with a negative slope. Real gases are going to look slightly different because real gases do have mass, they do have volume. When you graph this data, if you're graphing experimental data, you tend to have a curve to it. So you're going to see the same basic trend. It's still going to be inverse. It's just not going to be perfect. And once we get to very low pressures or very high pressures, you can only compress the particles of the gas so much. You can only let them spread out so much. And then you start to see a shallower slope to your line. So mathematically, what does this look like? What do the questions look like? Remember, I want you to read the word problems, look for key numbers and units, make sure you know what they're referring to. So a 200 milliliter sample of a gas at 8 atms has its pressure reduced to 4 atms. If the temperature stays constant, what's the new volume? So I used two different colors there because this is what we're starting at. You're starting with a gas sample that's 200 milliliters. Milliliters is a unit that we use for volume. And it's at 8 atms. atms is a unit that we use for pressure. And then it's going to have its pressure change. So you're ending at 4 atms. Again, that's going to be your new pressure. And they want to know what the new volume is. So now all we have to do is plug our numbers in. 200 times 8, because remember we're just going to ignore temperature, so we're going to use this combined gas law version, ignoring temperature, and then we have 4 times x. So 8 times 200 gives us 1600 equals 4x. Divide both sides by 4, and x equals 400. The next thing I want you to do is ask yourself, does this make sense? If this is Boyle's law, because we're talking about pressure and volume, and I know Boyle's law is an inverse relationship, Does it make sense that if I decrease the pressure, I've increased the volume? Yes, it does, because that would be inverse. I reduce one, I must increase the other. I must have set that up correctly. My math is good. All right, next problem. A 100 milliliter sample of a gas is enclosed in a cylinder under a pressure of 75 kPa. What volume, so that's what they're looking for, is volume, would the gas occupy at a pressure of 150 kPa, assuming the temperature remains constant? So again, we're going to use PV equals PV because we're ignoring temperature. Temperature was constant. 100 for my starting volume, 75 for my starting pressure. I don't know my ending volume, 150 for my final pressure, and then we just do the math. So we have 7,500 equals 150x. Divide both sides by 150. And I don't feel like doing that in my head this morning, so just to make sure I get the right number, 7,500 divided by 150, 50. And so then I ask myself, all right, if x equals 50, does this make sense? What was I looking for? A volume. They started with milliliters, so this must be in milliliters. And then I say, does this make sense? They've increased the pressure. So if it's an inverse relationship and they increase the pressure, my volume should go down. Increased pressure, decreased volume. So I look, and yes, it went from 75 to 50. The volume went down. This must be okay. I must have done the math correctly. All right, on to Charles's law. Charles's law is going to be the relationship between the temperature and volume of a gas. If you've ever played with helium-filled balloons, you've seen this. So if you grab a helium-filled balloon in the winter, it's not so obvious in the summer, but in the winter, if you buy a helium-filled balloon at the store, it's nice and warm in the store, and the balloon's pretty full. You take it outside to your car, and you put it in the back seat, and by the time you get home, the balloon's laying on the floor, and it looks like it's shriveled up, and it looks like it's lost some of its helium. You take it inside, you're angry, and then it warms up in your house, and the balloon puffs back out. That's Charles's law. The volume of a gas varies directly with the temperature. So as one increases, the other also increases. Helium is closer to an ideal gas, so you're going to definitely see this change in volume with temperature much better with a helium-filled balloon than you will with a balloon you just fill up with air from your lungs. Not so obvious if you just take a regular balloon outside in the winter. But at winter ball, if you grab one of those helium-filled balloons and you take it outside for a little while, the volume in the balloon will definitely decrease. What does a graph of Charles's law look like? Well, it's a direct relationship. So if I have volume and temperature, it's a direct relationship. So if I have volume and temperature, as one increases, the other also increases. An ideal gas, you're going to have this perfectly straight line with a positive slope. Again, real gases don't have the same conditions. They do have volume, they do have mass, they do attract each other. So a real gas, you're probably going to have a curve to it, just like you did for the Boyle's law. Direct relationship, straight line. If we look at this proportion, V1 over V2 equals T1 over T2. It's a direct relationship, so your initial volume and your initial temperature, both at the top, your ending volume and your ending temperature, both at the bottom. That will be the same as the equation that we find on reference table T. Combined gas law equation, here it is. It says to ignore what remains constant. So if this is Boyle's law, we're going to ignore pressure. So we're just going to cross pressure out, and we get V1 over T1 equals V2 over T2. This is going to be the same equation. It's going to mathematically be the same as V1 over T1 equals V2 over T2. We've just done some algebra and rearranged the parts. So it really doesn't matter which equation you use. The proportion, you would have to memorize and set up the proportion correctly. The combined gas law one is just on your reference table, and you ignore pressure. So this is the one that I use, and it's the one I recommend you use. Mathematically, if you love proportions, go for it. All right, so let's look at the examples. A gas occupies a volume of 500 milliliters at 700 K. If the pressure remains constant and the temperature is increased, so we're going to increase the temperature to 2100 K, what is the new volume of the gas? Okay, so this is a volume. That's where we're starting. That's our starting temperature. They want to know what the ending volume is if we increase the temperature to 2100 K. Notice something super, super important here. Super, super important. This used to be stated on your reference table itself. It no longer says it. The temperatures for the gas laws have to be in Kelvin. Because we have temperature in the denominator, you're not going to be able to put a negative number down here and have it work out okay. It has to be in Kelvin. They will make some of the questions harder by giving you the temperatures in degrees Celsius, and you need to convert them into kelvins. But the temperatures must be in kelvins. Temperature in kelvins only for gas laws. All right, so let's plug these guys in. We're starting with 500 milliliters. It's at 700 K. They want to know what the volume will be at 2100, and then we cross multiply. So we have 500 times 2100 equals 700x. Again, not doing that in my head, so let's grab our calculator. 500 times 2100. 1,050,000. And then divide both sides by 700. And I get 1,500. What units did they use for their original volume? They used milliliters, so the units here will be milliliters. Again, once you're done, you want to ask yourself, does this make sense? If I have increased the temperature, I've tripled the temperature, my volume should increase because it's a direct relationship. 1,500 is definitely bigger than 500. It's 3 times bigger. That makes sense. I must have done my math correctly. All right, look at this next problem. This is one of the ways you're going to make the problems a little bit harder. It says a 2-liter gas sample at STP is cooled to, so they're going to change the temperature to 62.25, assuming the pressure stays constant. What is the new volume of the gas? And at first you're like, they only gave me 2 numbers and I need 3 out of the 4. Right here, this STP. Remember, on reference table A, here's your STP. Standard temperature, right here, 273 kelvins. So when we look at this, that's really saying that my starting temperature is 273 kelvins. So I have 2 liters over 273 kelvins equals X liters over 68.25 kelvins. Pull up the calculator. 68.25 times 2 equals, divide that by 273, and I get an ending volume of 0.5. And the units that they started with for their volume this time were in liters, so this must be 0.5 liters. Last thing you should do is ask yourself, does this make sense? If they've cooled it from 273 to 68, they've decreased the temperature. The volume should decrease also because this is a direct relationship. 0.5 is definitely less than 2. You probably set it up correctly. And the last one is this Gay-Lussac's law, pressure and temperature. Also, if you look at its equation, either here, P1 over P2 equals T1 over T2, that is a direct relationship. Also, if you look at table T, and we just ignore volume this time, here it is, volume's constant, It looks like the same equation as the Charles's law, so also a direct relationship. It would also have a graph that goes up with a positive slope. This one doesn't get tested very often, and you don't need to know its name. The only ones you need to know the name of by name and what conditions they are Boyle's law and Charles's law. Moving on away from the gas laws and on to other concepts when it comes to gases, we're going to start with partial pressure. In partial pressure, the really hard concept here is that the sum of the parts equals the total. And that's really it. So if you have a mixture of gases, and there's more than one type of gas in there, if you add up all of their partial pressures, then it would have the total atmospheric pressure of that sample. This is how a breathalyzer works. They know what the partial pressure is of the nitrogen, of the oxygen, of the carbon dioxide, and of ethanol. So by testing the partial pressures, the pressure of the vapors coming out of your lungs, it can tell how much alcohol is in your system. So total pressure, sum of all of the parts. So if we just look at a quick problem, the total pressure exerted by a mixture of gases is the partial pressure of one gas is 75, and the partial pressure of another is 25. So the total is just going to be the sum of those two. So the pressure total, that's what the little sub t means, 75 plus 25, your total pressure would be 100 kPa. Nothing huge or stunning or difficult about that, just add them up. Okay, now one of the things that happens though is that because of the way this is set up, we can do percents with it. Percents are going to be super important in chemistry. Percent is going to be part over the whole amount, and then we just multiply it by 100%. Okay, so it's a ratio, and it becomes really important. It's going to help us identify things. It's going to help us do lots of math with our chemistry, and it's really pretty simple. So if we look at a partial pressure question, like this example, it says a 300 milliliter container is filled with 100 milliliters of oxygen and 200 milliliters of hydrogen. So we know that a gas is going to fill up its container. So the 100 milliliters of oxygen, 200 milliliters of hydrogen, the total is our 300 milliliter size container. The question goes on. It says it has a total pressure of 2 atmospheres, and it wants to know what is the partial pressure of just the oxygen. So the first thing I would have you do is ask yourself, well, what percent is oxygen? So to find the percent that's oxygen, what part is from oxygen? Well, the 100 is from oxygen. What's the total volume of our sample? The total is 300. So we have 0.3% or 0.3 or 30% oxygen. So if your total pressure is 2 atmospheres, and I take that 2 atmospheres and I multiply it by 30%, and I always prefer to leave it as a decimal, so I'm going to multiply. If you're multiplying by 30%, I'm multiplying that by 0.3. 2 times 0.3 is 0.6. And the units are ATMs, because that was the unit on the 2. And that's it. We're just doing percents. There are going to be other ways to measure gases besides volume in milliliters. We're going to have this concept called a mole. So sometimes they're going to report amounts of chemicals and amounts of gases to you in moles. So this example says a sample contains 8 moles of nitrogen and 2 moles of oxygen. If the sample is at STP, here's that pesky STP again. Remember, STP stands for standard temperature and pressure. They want to know the partial pressure of the oxygen in atmospheres and in kPa's. So our first step might be to figure out what is the original total pressure in atmospheres and in kPa. So STP on table A. STP, here's our pressures, 101.3 kPa's, 1 atmosphere. That's our standard pressure. So total pressure is going to be either 101.3 kPa's or 1 atmosphere. The next thing I need to know is what percent of this mixture is oxygen. So we want the partial pressure of the oxygen. We are going to figure out what percent is oxygen. So the part that's oxygen, is 2 moles. And our total sample, or our whole amount, let's call it the whole amount. The whole amount is going to be the 8 plus the 2, or 10 moles. So 2 out of 10 means that I have 0.2 or 20% oxygen in this sample. So if I want to know the pressure of the oxygen in atmospheres, I'm going to take 1 atmosphere and multiply it by 0.2, or 0.2 atmospheres. And if I want to know the partial pressure of oxygen in kilopascals, I'm going to take 101.3 kPa's and multiply that by 0.2. And that one I don't want to do in my head, so we get out our trusty calculator. 101.3 kPa's times 0.2, or 20%, and I get 20.26. 20.26, and the units here are kPa's. If most of the mixture is nitrogen, most of the pressure should come from nitrogen. So I should have a number that's pretty low for the oxygen. It is a relatively low portion. I probably did my math correctly. If the partial pressure information really confuses you, don't panic. Partial pressure is an extra. It's an enrichment. There are not going to be final exam questions on partial pressure. I might ask you about it because percents are really super important in chemistry, and it's another good way to practice your percent work, but don't panic. You're not going to find final exam questions on it. Last couple of pieces here. Graham's law is a concept that says, and this is a really difficult one, it says that heavy gases move slow, and light gases move fast. So when you talked about diffusion, you talked about diffusion in biology. Particles always move from areas of high concentration to areas of low concentration. How fast that happens with gases depends on how heavy they are. So we have this concept of atomic or molecular mass. On your periodic table, there are masses in the corner. So if we have carbon, carbons are key all the time, 6 down there, and then it says 12 point something up there, 0001. This number up here at the top, this one right here, is its atomic mass. The first thing I want you to do is round it. So round it to a whole number, and we'll discuss why we do that later, but for right now, just trust me and do it. We round it to a whole number. That's going to be its atomic mass. For a compound, we add up all of the masses of all of the pieces in it, and we see how heavy it is. So over here to the side, sulfur dioxide. Sulfur dioxide, SO2. I say there's 1 sulfur, because remember there's a little 1 here, and there are 2 oxygens. This subscript only carries through to the first capital letter right after it. I would look on my periodic table at these numbers to speed things up. I'm just going to give them to you today. Sulfur has an atomic mass of 32, and each oxygen has a mass of 16. If I have 1 sulfur with a mass of 32, that's 32. 2 oxygens at a mass of 16 each, that's 32. I add them up, and I get 64. So sulfur dioxide has a mass of 64 AMUs. Methane. Methane is CH4. That's one of the few common names of an organic molecule that you'll see a lot even before we get to organic chemistry because it's so common. This is the natural gas. It's the stuff that we're burning in our burners. So if we look, methane is made of 1 carbon and 4 hydrogens. So I already showed you here, carbon has a mass of 12, and hydrogen is really super tiny. I talked about that up top when we were talking about ideal gases, that hydrogen has a mass of 1. If there's 1 carbon with a mass of 12, that's 12. If there are 4 hydrogens with a mass of 1 each, that's 4. I add those two together, and it has a mass of 16. So methane has a mass of 16 AMUs. Last but not least, ammonia. Ammonia is a common name. If you look on reference table L for the bases, ammonia is a very common base. It's NH3. It's made of 1 nitrogen and 3 hydrogens. Each nitrogen has a mass of 14, and each hydrogen again has a mass of 1. 1 nitrogen at 14 is a mass of 14. 3 hydrogens at 1 each is a mass of 3. So ammonia has a total mass of 17 AMUs. So the question wants to know which one diffuses the slowest. Well, heavier moves slower, smallest move faster. So our answer to this question would be number 1, sulfur dioxide. That's a lot of work for one multiple choice question. The state does this a lot on your chemistry exam. Notice that you not only have to understand Graham's law, and that the heaviest gases move slowest and the lightest gases move fast, but you have to know how to convert all of these compound names into their formulas. So you have to know that sulfur dioxide is SO2, and methane is CH4, and ammonia is NH3. And then you have to be able to add up their formula mass. So you have to be able to count the pieces in your formula. You have to know where to find their masses on the periodic table. And then you actually have to do the algebra. So they can test you on quite a few of our chemistry concepts in this one really simple multiple choice question. Chemistry is going to be a lot of applied questions. It's just the way that it is. I know it's more difficult, so you just need to practice and look at a lot of them. Okay, last concept for gases, and then we'll move on to solids and liquids in the next lecture, is this idea that the density is somehow related to how many moles there are. So moles are a unit in chemistry. They're a way of measuring pieces. Scientists have found out that gases all have a volume where 1 mole equals 22.4 liters. 1 mole is also going to be equal to a compound's formula mass in grams. So if I had methane and I measured out 16 grams of methane, I would have 1 mole of methane. And they know that 1 mole, if they're counting numbers of pieces, is 6.02 times 10 to the 23rd pieces, or units, or atoms, or molecules. That's a very large number. So if you have 16 grams of methane, it's going to have a volume of 22.4 liters, and it's going to contain 6.02 times 10 to the 23rd pieces. So a mole is a really important concept here. The question, however, is just factor label. This question is just dimensional analysis, or factor label. So if you look, they want to know what is the gram molecular mass of a gas that has a density of 2.5 grams per liter. So if I have 2.5 grams per liter, and I know this relationship right here, if I put my 22.4 liters on the top and my 1 mole on the bottom, when I multiply, liters are going to cancel. Grams don't cancel with anything. Moles don't cancel with anything. So I grab my calculator and I multiply 2.5 times 22.4, and I get 56. And the units that I'm left with are grams per mole, and those are the units for gram molecular mass. Gram molecular mass is done in grams per mole, or this relationship right here, grams per mole. Grams, formula mass, per mole. And that's it. It's just dimensional analysis. We just do that work, and we get our answer of 56 grams per mole. Why do scientists care about this? Well, if you're trying to identify an unknown gas, you can find its density in lab, put it in a balloon, measure its mass, find the volume of the inside of the balloon. You can find its density, so that's easy to do experimentally. You've been doing density for a long time. You can multiply it then by 22.4 liters per mole. Your gas has to be one of the gases that has a formula mass of 56 grams per mole. So it might not completely identify your compound, but it's at least going to narrow your choices down quite a bit. Look at all the ways we apply math and chemistry. All right, math's great. Chem's going to use a lot of it. Take your time. Don't panic. It's just algebra. Next lecture, we're moving on to solids and liquids.